In this video, we are going to learn what is telescoping series. So before we start with the standard problems on telescoping series, let us formally define what exactly is a telescoping series. So the formal definition of a telescoping series is: a telescoping series is a series whose partial sums eventually only have a fixed number of terms after cancellation, and this particular cancellation technique, where the part of each term cancelling with the part of the next term, is known as the method of differences. So to understand this definition in a better way, let's take one example of a standard telescoping series. Let us discuss this problem on telescoping series. So this problem says that evaluate summation r equals 1 to n 1 by r into r plus 1. So we can rewrite this as summation r equals 1 to n, this particular fraction as 1 by r minus 1 by r plus 1. And now if we break this summation, which means that if we just simply put these values, so this becomes 1 by 1 minus 1 by 2 plus 1 by 2 minus 1 by 3. Then the next term would have been 1 by 3 minus 1 by 4, and so on up to 1 by n minus 1 by n plus 1. So if we carefully see, this term gets cancelled, minus half gets cancelled with the next term of plus half, then minus 1/3 gets cancelled with the next term of plus 1/3, and similarly minus 1 by 4 will get cancelled with the next plus 1 by 4, and so on. So this process of each term cancelling with the part of the next term is known as the method of differences, as we have seen in the definition. So half gets cancelled, 1/3 gets cancelled, this 1/4 will just get cancelled with the next term, and similarly this 1 by n will also get cancelled. So the remaining terms will be 1 and then minus 1 by n plus 1. And this will be the answer. Suppose this problem would have said that evaluate summation r equals 1 to infinity 1 by r into r plus 1. So instead of n, we have r equals 1 to infinity. So now let's see. So here we take limit n tends to infinity, summation r equals 1 to n 1 by r into r plus 1, and then we solve exactly in the same process, in the same procedure like what we have done here. We do the same procedure, only here only on the last line we just simply plugging the limit. So which means that this is simply limit n tends to infinity 1 minus 1 by n plus 1. So this is just simply 1. This term, this becomes 0, this becomes 0, and so basically we are left with 1. If limit n tends to infinity, 1 minus 1 by n plus 1 is just simply 1. So the summation r equals 1 to infinity 1 by r into r plus 1. The value of this is simply 1. So let us now see this particular problem, which says evaluate summation n equals 1 to 2015 1 by n square plus 3n plus 2. So first of all, let us simplify this. This is basically n equals 1 to summation n equals 1 to 2015 1 by n plus 1 into n plus 2. And then similarly we have to write down this in terms of partial fractions, which means that n equals 1 to 2015, this is basically 1 by n plus 1 minus 1 by n plus 2. So now if we break this summation, this particular summation, now what we get, so from here if we put these values, so we get half minus 1/3, then plus 1/3 minus 1 by 4 plus 1 by 4 minus 1 by 5 and so on, up to this will go up to 2001 by 2016 minus 1 by 2017. So again, if we carefully see, there is a similar process. So a similar sum. So 1/3 gets cancelled, 1/4 and 1/4 will get cancelled, and so on. So 1 by 2016 will also get cancelled at the end. So we are only left with half minus 1 by 2017. So half minus 1 by 2017 is basically, this is 2017 minus 2, which is 2015, divided by 2 into 2017, which is around 4034. So now let's see this problem, which says if Tn is 1 by 4 into n plus 2 into n plus 3 for n equals 1, 2, 3 and so on, then we have to find the value of 1 by T1 plus 1 by T2 and so on up to 1 by T2020. So basically we have to find this particular value. So if we carefully see, this 1 by T1 plus 1 by T2 and plus 1 by T3 and so on up to 1 by T2020, this is nothing but this is basically, this particular expression can be written as summation n equals 1 to 2020 1 by Tn. So now let's see, since Tn is given in the question, now let's see. So Tn is basically 1 by 4 into n plus 2 into n plus 3. So if Tn is this, then what is 1 by Tn? 1 by Tn will be 4 upon n plus 2 into n plus 3. Now if we put summation both sides here in this particular expression, like the summation will run from n equals 1 to 2020, since basically they have said in the question that we have to solve summation n equals, we have to find the value of summation n equals 1 to 2020 1 by Tn. So here in this particular equation, we simply put summation on both sides. So this is summation n equals 1 to 2020 1 by Tn equals summation n equals 1 to 20, 4 upon n plus 2 into n plus 3. Now again in partial fractions, this turns to n equals 1 to 20. This is if you just simply, now 4 is a constant, you can simply take 4 outside the summation. So this turns to 1 by n plus 2, then minus 1 by n plus 3. So this is summation n equals 1 to 20, 1 by Tn is basically 4 into, now if we break this summation, this turns to 1/3 minus 1/4, and then we have plus 1/4 minus 1/5, and so on. Like this, we have up to 1 by 2022 minus 2023, which is, so basically you're left with summation n equals 1 to 20, 1 by Tn. Now here we are left with what? So 1/4 gets cancelled, 1/5 and 1/5 will again get cancelled. We are left with the first one, which is 1/3, and then we are left with minus 1 by 2023. So this is basically 4 into 1/3 minus 1 by 2023. Now if we calculate this one, this is around, so 4 into now 2023 minus 3, which is just simply 2020 divided by, this is 3 into 2023. Now this is around, so this is 4 into this, which will be around 8080 divided by, now 3 into 2023, which is 6069. So the summation this equals, so the complete answer is 8080 divided by 6069 is the value of the summation. So let us see this problem. This question says that summation k equals 1 to n 2k plus 1 divided by k square plus k the whole square equals 0.9999. So what we have to find? We have to find n. This problem was asked in IOQM 2020. So let us solve this one. So this is summation k equals 1 to n. In the denominator, we can take k common. So this becomes k square into k plus 1 the whole square. Now we try to bring the form of k plus 1 the whole square in the numerator. So for that, we add k square and subtract k square in the numerator. So if we add k square, then this numerator becomes k square plus 2k plus 1, which is k plus 1 the whole square minus k square. So now see here, now we divide this individually. So this becomes 1 by k square minus 1 by k plus 1 the whole square. So this is a very common telescoping series. We have done this quite a few times. So this is 1 by 1 square minus 1 by 2 square plus 1 by 2 square minus 1 by 3 square plus 1 by 3 square minus 1 by 4 square, and so on up to 1 by n square minus 1 by n plus 1 the whole square. So this is 1 minus 1 by n plus 1 the whole square. Clearly we can see these terms are getting cancelled. So we will be left with only this term and this term. 1 by n square will also get cancelled. And this sum is given to be 0.9999. Here it's given in the question. So now let's solve this one. We now solve for n. So this is 1 by n plus 1 whole square. So this is 0.0001. So n plus 1 the whole square. Now if we take reciprocal on both sides, so this is 10 to the power minus 4. So this becomes 10 to the power 4. And 10 to the power 4 is same as 100 square. So n plus 1 is 100. So n is 99. So the value of n is 99. Okay, now let us see one more problem. So here this problem says we have to find the sum of n terms of this series 1 by 1 plus 1 square plus 1 to the power 4 plus 2 by 1 plus 2 square plus 2 to the power 4. So the next term will be 3 by 1 plus 3 square plus 3 to the power 4 and so on. So we have to find the sum of n terms. So before we start the problem, so what we do, we first represent this in terms of sigma. So this is summation or sigma r equals 1 to n r by 1 plus r square plus r to the power 4. So this is the sigma representation of this series. Now let us see how we bring this into the form of a telescoping series. So this is summation r equals 1 to n r divided by, now very carefully see here, we add r square and subtract r square in the denominator. So why we are adding r square and subtracting one extra r square? Because if you see here, this part 1 plus r square plus r to the power 4 plus r square, which is 1 plus 2 r square plus r to the power 4. So this is nothing but summation r equals 1 to n r divided by, this becomes r square plus 1 the whole square, then minus r square. Now this is summation r equals 1 to n r by, now we can write this in the form of a square minus b square. So this is r square plus 1 minus this is in the form of a square minus b square, which is a plus b into a minus b. Okay. So now we will use the concept of partial fraction. So what we have to do to use the concept of partial fraction? So before we represent this into the form of a partial fraction, we have to make some adjustments. So we multiply with a half. So like we are taking one extra 2 in the numerator. So we are multiplying with a half in the front. Now why we are taking this 2 in the numerator? Let us see. Now if we represent this in the form of partial fraction, this is summation r equals 1 to n. This is 1 by r square minus r plus 1, and then this is minus 1 by r square plus r plus 1. If you see in the numerator, if we evaluate these parts, this one and this one, in the numerator what we'll get? R square plus r plus 1, and then minus r square plus r, and then minus 1. So 1 will get cancelled. R square and R square will get cancelled. So we will be left with only 2R. Now to cancel out that 2, we are multiplying with a half in the front. So now this is a telescoping series. So this is half multiplied by this. So if we put 1, R as 1, so this is 1 by 1 minus 1 by 3 plus 1 by 3 minus 1 by 7 and so on. This is 1 by 7 minus 1 by 13, and this will go up to 1 by n square plus n plus 1 minus 1 by n square plus n plus 1. This will be minus. So clearly 1/3 gets cancelled, 1 by 7 and 1 by 7 gets cancelled, and so on. So half multiplied by this one and this term will be remaining, and that will be the final answer. So let us see few more trends of problems. This problem says evaluate this summation r equals 1 to infinity tan inverse 1 by 2r square, and this is given to be t, so we have to find the value of t. Remember that whenever we see tan inverse of something and we have a summation before, remember that in this case, in most of the cases, we have to bring this into the form of some formula involving tan inverse of x. Let us see. This is summation r equals 1 to infinity tan inverse of 1 by 2r square. So this is summation r equals 1 to infinity. Now tan inverse of 1 by 2r square. So this is, so here I multiply 2 in the numerator and in the denominator. So this becomes 2 by 4r square. Now let us see in the denominator. R equals 1 to infinity. This is tan inverse of 2 upon. Now I'll add 1 and subtract 1 in the denominator. So why we are doing this one? Because this 4r square minus 1 turns to tan inverse of 2 by 1 plus this 4r square minus 1 can be written in the form of 2r minus 1 and then 2r plus 1. Why? Because in the numerator summation r equals 1 to infinity tan inverse of, now this 2, this particular 2 in the numerator can be written as 2r plus 1 minus 2r minus 1 and divided by 1 plus 2r minus 1 multiplied by 2r plus 1. So carefully in the numerator, if I simplify the numerator, this is 2r plus 1 minus 2r plus 1. So clearly 2r gets cancelled. We are left with plus 1 and plus 1, which is 2. So that is what we are getting in the numerator. So why we have done this? As I said, our main target is to bring this into the form of some formula of tan inverse of x. So this is summation r equals 1 to infinity. Now this is tan inverse of 2r plus 1 minus 2r minus 1 divided by 1 plus 2r minus 1 multiplied by 2r plus 1. How much is that? Tan inverse 2r plus 1 minus tan inverse 2r minus 1. This is of the form tan inverse A minus tan inverse B. So this is tan inverse 2r plus 1 minus tan inverse of 2r minus 1. So we have discussed this before as well. Whenever the series tends to infinity, whenever we have summation r equals 1 to infinity, this means that the series is tending to infinity. We will simply take limit. So this is limit n tends to infinity, summation r equals 1 to n, tan inverse 2r plus 1 minus tan inverse 2r minus 1. So now let us see. This is limit n tends to infinity, and this series is tan inverse 3 minus tan inverse 1. Next term will be tan inverse of 5 minus tan inverse of 3. Let me write few more terms. The next will be tan inverse of 7 minus tan inverse of 5, and so on. So the last term will be tan inverse of 2n plus 1 minus tan inverse of 2n minus 1. So clearly it's a telescoping series. So tan inverse 3 gets cancelled. Tan inverse 5 will get cancelled. Similarly, tan inverse 7 will also get cancelled. And likely we have tan inverse minus of tan inverse 2n minus 1. This will also get cancelled. So we will be left with only limit n tends to infinity tan inverse 2n plus 1 minus this tan inverse of 1. So how much is limit n tends to infinity tan inverse of 2n plus 1? Clearly it is pi by 2, because when n tends to infinity, this inside expression tends to infinity. So tan inverse of infinity is pi by 2. And we can put the limit over here as well. We know that limit is distributive, but since tan inverse of 1 is a constant, so tan inverse of 1 is pi by 4. So this is pi by 2 minus pi by 4. So the value of t is pi by 4, because the series was given to be t. So what is t? T is pi by 4. Okay, so let us see one more similar problem. This problem says evaluate this summation r equals 1 to n tan inverse 2 to the power r minus 1 divided by 1 plus 2 to the power 2r minus 1. So as I said before, whenever we have this summation of tan inverse of something, we try to bring this in the form of some formula of tan inverse function. So let us try to solve this one. This is summation r equals 1 to n tan inverse of, now carefully see here, we write this 2 to the power r minus 1 as 2 to the power r divided by 2, and here we write this 2 to the power 2r minus 1 in the form of 2 to the power r multiplied by 2 to the power r minus 1. And why we are doing so? See, we can further write this as summation r equals 1 to n tan inverse. We can write this 1 by 2, this half, as 1 minus half. If we write this as 1 minus half and then we multiply with 2 to the power r, this becomes 2 to the power r minus 2 to the power r minus 1 divided by 1 plus 2 to the power r multiplied by 2 to the power r minus 1. Now this is of the form of tan inverse A minus tan inverse of B. So this is summation r equals 1 to n tan inverse 2 to the power r minus tan inverse of 2 to the power r minus 1. Now let us verify whether this is a telescoping series or not. Now replacing the value of r, this is tan inverse 2 minus tan inverse of 1. The next term will be tan inverse 2 square minus tan inverse of 2. The next term will be tan inverse 2 cube minus tan inverse 2 square, and so on. This will go up to tan inverse 2 to the power n minus tan inverse 2 to the power n minus 1. So how much is this? So clearly tan inverse 2. So here we have tan inverse 2, tan inverse 2 gets cancelled, right? Similarly, tan inverse 2 square, tan inverse 2 square gets cancelled. So if we see, we are left with only tan inverse 2 to the power n minus tan inverse of 1. So we have done before also. Clearly we can find limit n tends to infinity also. Limit n tends to infinity also very easy to find. So these are some of the new trends of problems where you will be having a tan inverse of some functions. So remember that we always try to bring this into the form of some formula of tan inverse of x. Okay, so let us see one more standard problem from telescoping series. This problem says Fn be the Fibonacci sequence which is defined by f0 equals to f1 equals to 1. And the definition of Fibonacci sequence is given by fn plus 2 equals fn plus 1 plus fn for all n greater than or equals to 0. So we have to prove that summation k equals 1 to n 1 by fk minus 1 into fk plus 1 is less than 1. So let us see how to solve this problem. So we have summation k equals 1 to n 1 by fk minus 1 multiplied by fk plus 1. So we have for all k greater than or equals to 1, we have 1 by fk minus 1 multiplied by fk plus 1. Now we have to make some adjustments before we bring this into the form of telescoping series. We multiply with fk in the numerator and in the denominator. Fk minus 1 multiplied by fk, then multiplied by fk plus 1. And what is the one more representation of fk? Here in the definition of Fibonacci sequence, if we replace n by k minus 1, we will get one more relation of this Fibonacci sequence in terms of k plus 1 and k minus 1. What I mean to say is, if we replace n by k minus 1, this becomes fk plus 1 equals fk plus fk minus 1. So what is fk from here? Fk is clearly fk plus 1 minus fk minus 1. So we can put this value of fk over here in the numerator. So this is fk plus 1 minus fk minus 1 divided by fk minus 1 multiplied by fk multiplied by fk minus 1. This was fk plus 1. So clearly now we can divide this individually. So this becomes 1 by fk minus 1 into fk minus 1 by fk multiplied by fk plus 1. So now this summation becomes summation k equals 1 to n. Clearly this is a telescoping series. Now how to write this one? This is fk minus 1 into fk plus 1. So this is 1 by f0 f1 minus 1 by fn multiplied by fn plus 1. The first term and the last term will be remaining. So how much is this? What is f0 and f1? f0 and f1 is given to be 1 by the definition of your Fibonacci sequence. So this is 1 minus 1 by fn multiplied by fn plus 1. So what is 1 minus fn? 1 minus 1 by fn multiplied by fn plus 1. This is always less than 1 for all n greater than or equals to 1. So hence we have proved this.